Thank you.
Yep.
All right, we left off with this slide. We were talking about making solutions. Concentrations are important so that we know what's there, how much moles of solute is present, because that's going to determine how dangerous or how much something's going to react. We started with by mass solutions, and the last thing I asked was how would we make, for example, how would you prepare 250 grams of a 5% by mass glucose solution? In other words, normal glucose. What do I know about my final solution? What must be true about it? It's going to have to weigh what? My final solution, how much do I want it to weigh? Look at the problem. 250. It says, how would you prepare a 250 grams of a 5% by mass glucose solution? Okay, so that means I want my final solution to be 250 grams. Now, if I want that final solution to be 250 grams, which is going to be roughly close to 250 milliliters, because it's not going to be far off of the density of 1, how am I going to go about doing that? Well, first thing I'm going to do is get a container and do what with it? Put it on a scale. Okay, I can tare it, put it on a scale, and then I'm going to add my stuff to it until, in the end, it weighs 250 grams. Okay? The first thing I want to figure out, though, is we know we're going to use water to dilute all of this. I need to know how much sugar I put in, how much glucose is put in, and then I'll fill the rest of the way up with water. So how do I figure out how much sugar I want to put in? I want 5% by mass glucose. So 5% in terms of grams compared to the total grams of the solution. So 5% by mass, you would have to figure out what's 5%, right, of this total situation. So if I have 5% means of 100, right? So that means if I had to represent a conversion factor for 5%, that would be the same thing as 5 grams of glucose in 100 grams of solution, even though I want 250 grams of solution. So that means I can start with 250 grams of solution, realize that I want to set up a scenario where I have the equivalency of 5 grams for every 100 grams of solution that's present, so I can use that as a conversion factor. What that tells me is that I need 12.5 grams of glucose. Now, when you guys did this in your head last time, you said, okay, I got 250 grams. I know that for every 100 grams I have, I need 5 grams, right? So if I've got 5 for 100 grams, plus 5 more for the next 200 grams, for the next 100 grams, that's 10. Then I've got 50, which is half of that, so that's 2.5, so I add it all together. Well, that might be fine in this situation, but numbers aren't that easy. Okay, they're going to be a little more complicated than that. So be able to do the same thing except through mathematical steps. Realize that you're taking 250 grams. You know that a 5% solution can be represented like this. So cancel out what cancels out. There you got 12.5 grams of glucose. So what do? Okay, probably in a container, but yeah. Okay, that's right. And then I'd stir it all around while I'm doing, make sure it all dissolves. All right. We call this QS. QS stands for quantity sufficient. If you ever make solutions, that's what we'll say. I will say dissolve 12.5 grams of glucose, QS to 250 grams. That means you're going to then, after you dissolve your 12.5 grams of glucose, or after you place your 12.5 grams of glucose on there, what you're going to do is add enough water until your quantity is sufficient to 250 grams. That's what QS means. Okay, one way to express concentration was percent by mass, what we just did, like a 5% solution. In chemistry, a more useful way, so that we can keep track of the actual number of moles of solute particles that are present, is a concept known as molarity. Okay, it's symbolized by a capital M for molarity. What it stands for is how many moles of solute are dissolved in a given 1 liter of solution. Okay? We need to be able to keep track of how many individual molecules. If you're reacting two things and you know you have this much of reactant A, this much of reactant B, one way that you can keep track of that is to keep track of its concentration. If you know what its concentration is and what volume you have of it, likewise over here, you can figure out how many moles are present, and you can see how they're going to react in terms of reaction stoichiometry. So this is useful, okay? If a sugar solution concentration is 2 molar, that means if you had 1 liter of it, you should be able to count 2 moles of sugar. That's what it means. If you had 2 liters of it, if it was 2 molar, that means it would be 2 moles for every liter. So if you have 2 liters, you should have 4 moles of that sugar present total. If you had half a liter, that means you should have 1 mole of sugar present. Okay? 2 molar means the ratio is if you have 1 liter, you would have, in this case, 2 moles. If you have half a liter, then you would have 1 mole. Okay? So it's just a way to express that. You don't have to always have your volume be 1 liter, but that's your reference point. Okay? All right. So molarity then is defined as moles of solute per liters of solution present. So then, how do you prepare a 1 molar sodium chloride solution? Sodium chloride is obviously a solid in its normal form, a salt. You're going to have to dissolve it. The key here is, if I asked you in lab to prepare 1 molar sodium chloride, it's because I want you to make sure you get a specific amount of sodium chloride ions present to make this chemical reaction occur. We need at least, they say, this much. Okay? So 1 molar means that's how concentrated I need it to be. If you have less than that, the reaction might not work very well. So, how do you prepare a 1 molar solution? Can you weigh out moles? No. What can you weigh out? Grams. Can you convert between grams and moles? Yeah, theoretically. Maybe not. Some of you still haven't got that far, but you can certainly theoretically convert between grams and moles. Okay, so that means, what does this, remind me, what does this big M mean? What does it stand for? What units? Like what is it? Moles per liter. So if you're going to make a 1 molar sodium chloride solution, you're going to need a volume, and you're going to need to know how many moles that's going to represent, right? So take a look. There are things called volumetric flasks that we can use in the lab. Probably the most calibrated piece of equipment that we can have. It looks simple, but it's actually very precise in terms of its measurement. There'll be a little line. You can't see it on here. On the next one, I exaggerate it. But there's a little calibration line, and it might say on here 250 milliliters or 500 milliliters or 1 liter. That's saying that if you fill it up to the meniscus to that line, it's exactly that amount, 250 milliliters. Okay? All right. So what you would want to do is, let's keep it simple. I didn't tell you how much of it I wanted. I just told you what concentration I wanted. You can make as much as this room will hold if you want to. I don't care. I just want you to make whatever it is you make, I want it to have that concentration, 1 molar. What's the easiest way to do it? Make 1 liter of it, right? No math. All you got to do is figure out what 1 mole is and put it in that liter and you're done. Okay? So in this case, make it easy. Let's just make 1 liter of this. So I would get a volumetric flask, because that way, in a graduated cylinder, you could do that, right? But you would have to pour it in and measure it, and it doesn't hold it very well, and you got all those tick marks. And it's easy to get a nice round number. You can actually get a liter flask with no markings on it. It's easy to carry, it's easy to store, it's easy to hold, and it's got 1 line on it, not a bunch of other lines. Fill it to that 1 line, you got 1 liter. Okay, it's that simple. So you've got to figure out how to get 1 mole of sodium chloride dissolved in a total solution of 1 liter. That's easy to do. All you got to do is figure out how much 1 mole of sodium chloride weighs in grams. So that's, if we know that if you take Na plus Cl, add them together, you get 58.45 grams. So we know that 1 mole of sodium chloride is 58.45 grams of sodium chloride. So all we got to do then is measure out. We don't have to do this on the balance this time, right? Because what we are measuring is volume, not mass. We're trying to QS to a volume, not QS to a certain mass. So we're going to weigh out 58.45 grams of sodium chloride, dump it in there. I weigh it on my weigh boat, I get 58.45 grams, then I dump it in my container. Then I can squirt it out a little bit with water to rinse off any extra that stayed behind and got stuck, because all I'm going to do is end up adding more water anyway, so the fact that I just squirted some in there is not going to make a difference. Okay? So now what you want to do then is QS all the way up to that 1 liter line. dissolving as you go. Probably what you want to do is fill it up about here and dissolve it. See if it'll go all the way, and then after it's dissolved, finish adding the rest of it. Okay? That's generally the safest practice to do. Okay, so then what you've done is taken 1 mole of sodium chloride, dissolved it in water to make enough solution to reach at this line, which is a total of 1 milliliter. You have a 1 molar solution now of sodium chloride. If you wanted a half a molar, a 0.5 molar solution, you would take half this much, right? You would have half that many grams. That would be half a mole. You would have 0.5 moles per liter, 0.5 molar. Okay? All right, so there you go. We've added the water. Here's our line, we'll say. Dissolve it, swirl it around, mix it, raise it up to that line, and you've got your solution. Then you label it just like this so that you know. Now with salt, not really going to hurt you, right? If this were some sort of crystallized acid that I was having you put into solution, this number becomes exceedingly more and more important, because the higher that number, the more moles of stuff you've dissolved in here, the more concentrated it's going to be. All right, so let's calculate molarity. We said it was moles per liter by definition. It says calculate the molarity of a solution if you made it by putting 15.5 grams of sodium chloride into a beaker and adding water to make a total of 1.5 liters of sodium chloride. You have everything you need to know. You need moles per liter to calculate molarity. Do you have moles? You do if you change this to moles, right? Do you have liters? Yes. So the only thing we have to do in this problem is figure out what this is in moles and divide it by 1.5 liters. We've got moles per liter, which is big M, molar. Okay? So that's what we're going to do. We know this is what we're getting at. We know that our molar mass is somewhere close to that, so we're going to use that to convert from grams to moles. So our mass of the solute, we're going to change that to moles of solute. Then we can take our volume that's already in liters, which is what we need. If it wasn't, we'd have to convert it. If it was milliliters, you'd have to convert it into liters. Okay? Molarity is moles per liter, not moles per anything else. We put those together, and we can get moles divided by liters to get our answer. So let's do that. Here's 15.5 grams of sodium chloride converted to moles. There's our mole value. Molarity is going to be that divided by our total liters, which is 1.5. So there's that. Here's our answer, 0.177 molar sodium chloride. Okay. All right. Another example that we can apply math to concentration problems. How many liters of a 0.114 molar sodium hydroxide solution contains 1.24 moles of sodium hydroxide? So what if you had an acid and you knew how many hydrogen ions were there? You knew that you had, because of other tests that you ran, 0.114 molar, or sorry, you had a certain number of hydrogen, a certain number of moles of hydrogen atoms. Okay, you needed to neutralize that. What? I guess here you need this. Let's say you had 1.24 moles of hydrogen present, and you wanted to completely neutralize it and react sodium hydroxide with it so that it cancels that out. An acid and a base, you add them together, you get a neutralization reaction, right? Let's say you have exactly 1.24 moles of hydrochloric acid. That means to neutralize it completely and most efficiently without any extra leftover stuff, you're going to need 1.24 moles of sodium hydroxide to balance that out. All right, well, let's say that you don't have sodium hydroxide sitting around except for one container, and in that container you have a bunch of it, but it's already been prepared and labeled at a certain concentration. It is 0.114 molar. You have a certain concentration of sodium hydroxide, and you can't waste it. You've got to save it for something else. So what you've got to figure out now is if I'm going to neutralize this, if I need 1.24 moles of sodium hydroxide, I know that I got it in this solution. But since I know how concentrated this solution is, I can theoretically figure out how much of it I need to pour out to get this many moles to land outside of that container. You follow me? You should be able to, if you know the concentration of something, you know that these NOH particles are in it, dissolved in it. The more concentrated it is, the less you have to pour out to get more moles. The less concentrated it is, the more you're going to have to pour out to pull more moles of that out, right? I need to get 1.24 moles of it out of there. How much do I pour out so that I can get 1.24 moles? That's the question, okay? All right, can we answer it? It's actually fairly simple because we know that it's moles per liter. All right, so we can use conversion factors here. We're given 1.24 moles. We're given the molarity. I want to know what would be the liters. You know, what would be the amount that I would need to associate with those values in terms of volume. Okay, so here's what I know. That's everything that I can write down that I know from the problem. I know that I have a concentration of sodium hydroxide that has, for every liter of that that's present, I've got 0.114 moles, right? So there's that written right there. That's another way to write the big M, moles per liter. Okay, so there's what I know. I know that I need to get 1.24 moles. So obviously now you can look and figure this out and see that I'm going to need more than 1 liter, right? Right now, if I just pour out 1 liter of this stuff, how many moles am I going to pour out? 0.114. I need 1.24. So obviously I'm going to need more than 1. I'm going to need more than 2. I'm going to need even more than 3 liters. It's a matter of calculating exactly how many liters am I going to have to pour out. Okay? So I know this to be true. Here's my concentration, moles per liter. Here's how many moles I'm trying to get to. How do I get there? I can go from, I'm given already moles of solute. Okay? I know how many moles right here that I have. I'm trying to get to total liter, that's the moles of solutes that's dissolved in this solution. I'm trying to get to the total volume of solution that I use to pour out. Okay? So I know that for every 1 liter of solution, because of my molarity, 1 liter of solution gives me 0.114 moles, like you just said. So put that down here, but arrange it so that things cancel out properly. Okay? That'll get me to this. If I take 1.24 moles, and here's my concentration, right? I know that for every 1 liter, there's 0.114 moles. If I do this math, this will cancel out. I'll be left with liters. I'll get an answer of 10.9 liters. That tells me that I need to pour in 10.9 liters to get enough sodium hydroxide that I need in this particular case. Okay? Questions about that? It's going to have to be a large vat. Yes. All right. Uh-oh. Looks like I already gave the answer. Okay. Again, another problem here. It says, how would you prepare 250 milliliters of a 0.20 molar sodium chloride solution? This is different because when I showed you the picture of preparing a solution before, it didn't matter. I didn't give you volume. You could just pick 1 liter if you wanted to. I didn't tell you how much to prepare. You could prepare whatever you wanted. What if you specifically need a certain amount? Okay? And you're forced to prepare only 250 milliliters because if you prepare more than that, you're going to get fired. Okay? They don't want you to waste stuff. So you only need 250 milliliters, and you need it to be that concentration. How are you going to make it? Now, if you can make 1 liter, this is easy to do. All you would need to do is, that's 0.20 moles for every liter, right? So you would just weigh out 0.20 moles, whatever that is in grams, and take it to 1 liter, and you're done. But I need 1/4 of that. I need 1/4 of a liter. That's 250 milliliters, right? So in your head, that's pretty easy because you could just take 1/4 of all of that. But realize that in real life, I've just picked these for simplicity of math. In real life, the numbers aren't going to work out that nicely. Okay? So how then, what you need to realize and think about is, okay, every time I see this letter right here, every time I see this concentration, I can use that as a conversion factor. That's moles per liter. So that means I take the other number that's present and figure out how to flip this thing around to make it work. That's pretty much all you got to do. In this case, I start with my milliliters. Okay, that's this in liters, right? Because this is in liters over here, so I have to make my units the same. So that would be 0.250 liters times this concentration right here. Okay, 0.2 moles per liter. That'll give me an answer in moles. That'll tell me. Now realize what I'm doing here. Let's backtrack. I'm preparing 250 milliliters of a 0.20 molar sodium chloride solution. What that means is when I'm done, my total solution, I should look at the line and it should be at 250 milliliters when I'm all done. And that means within that 250 milliliters, I'm going to have the same ratio as if I would have prepared a liter, I would have had to have 0.20 moles. So what I'm going to need is now a fourth of that, right? But it'll end up working itself out in the math. So what I'm trying to calculate here, what the point of this line is to figure out how much salt you're going to put in to get the proper concentration. It's not just 1 mole, right? It's actually less than 1 mole because we're not have a full liter. We have less than a liter. So we've got to figure that out. So here's our 250 liters. In that 250 liters, here's the ratio that we want to maintain. 0.20 moles for every liter. We don't have a full liter, but we can scale it down using this conversion factor. Okay, that'll give us moles. And if I stopped right there, that would tell me how many moles of sodium chloride I would have to put in and then dissolve to 250 milliliters. But we can't measure moles. So that's why this step is here. This is to tell us, take whatever this answer was in moles, turn it into grams, which is something I can actually measure and put on a scale. So you would get 2.9 grams. So I would weigh out 2.9 grams, dissolve it in enough water, in other words, QS 2.9 grams to 250 milliliters. Okay? So I'd grab an easy way to do it is grab a 250 milliliter volumetric flask, put it in there, to weigh out 2.9 grams, dump it in, squirt some of it off, rinse it off, and then add distilled water a little bit till about halfway up, swirl it all around, get it good and dissolved, and then put in the rest of the water until it reaches that line on the 250 milliliter mark. Okay, then I'm done. I've got 250 milliliters of a 0.2 molar sodium chloride solution. Now that's different, right? Because I would need 0.2 moles. If I would have left this out, this gives you that 1/4, that 25%, a quarter of what we started with kind of thing. Because if I was making it in just 1 liter, remember what I said? You would just take 0.20 moles per 1 liter. Then you'd have that right here and convert that. But 2.9 is less than what that normally would be because we've taken a fourth of it from over here. Okay? All right. Now, as far as what happens when we take things that are salts, like sodium chloride, and you drop it in water, the reason it dissolves, or what is happening, of course, it dissociates. The sodium and the chloride separate, and they move apart in the container, right? And for every 1 sodium chloride molecule, there was 1 sodium and 1 chloride, and they fell apart. Now, this is odd to think about, but think about this for a second. What happens if I have 2, no, let's just make it easy, 1. If I have 1 calcium chloride molecule, what is the formula for calcium chloride? Ca what? CaCl2. Right? Calcium's 2 positive, chloride's 1 negative, you need 2 chlorides. CaCl2. If I have 1 molecule of CaCl2 and I drop it in water, how many ions of how many ions of calcium are floating around? How many ions of chloride are floating around? 2. Notice what has just happened. Whatever concentration I would have started with for calcium chloride, when it dissolved, you should have that same value of concentration for the calcium. You should have twice that value for the chloride. You see why? It's split. It's separated. It is no longer part of the same entity anymore. It is now separated out into its components. So if I have calcium chloride, CaCl2, and let's say I have 1 molar calcium chloride, or I want to make, whatever. Let's say there's 1 molar value associated with calcium chloride. When that splits, there are still the same amount of calciums present free floating, right, as there was in the original molecule. So there's 1 molar of calcium in terms of its concentration. Chloride has went from being part of a 1 molar molecule. Since it split, there is now 2 that are freely floating. There's twice as much. It's 2 molar in terms of chloride at that point. Okay? I'll show you what I mean. Take this. Sodium chloride dissolves into that. So that means that the 1 molecule, remember it's really a formula unit. It's not really a locked together molecule. It's like an alternating 3-dimensional structure when we get into ionic compounds. One molecule will result in one ion of each of those. So that means it makes sense that if I had 100 molecules, it would result in 100 of those ions and 100 of those ions. Even further, if I had a mole of all of these, it would mean that I would have a mole of that and a mole of that whenever it dissociated. Okay, follow the logic. So that means if I had 1 mole per liter of sodium chloride, what I would have is 1 mole of sodium ions, 1 mole per liter of sodium ions, 1 mole per liter of chloride ions. Okay? So if I had 0.25 molar sodium chloride, my concentration of sodium would be 0.25 molar for chloride. Okay? Easy enough. Now, here's calcium chloride. CaCl2. What happens when it dissociates? 1 of these, 2 of those. Okay? 1 molecule of calcium chloride will give you 1 calcium ion, 2 chloride ions. So it stands to reason that if I had 100 molecules of this, I would have 100 ions of calcium, 200 ions of chloride. Even further, take it to moles. If I had a mole of calcium chloride, I would have 1 mole of calcium ions, 2 moles of chloride once it dissociated. Now, to get to concentration, notice how that makes a difference. At first, all this is together. So I have 1 molar CaCl2. What that really means with respect to each ion present is that I have 1 mole per liter of calcium, 2 moles per liter of chloride, because it's dissociated. Okay? So that same applies here. 0.25 molar for calcium chloride. Same, 0.25 molar for calcium, but twice as much, 0.50 molar for just the chloride ion by itself. All right, so without looking, figure this out. It says find the molarity of all ions in the given solutions of strong electrolytes. That means, strong electrolyte means they dissolve completely. They completely separate from each other. Okay? MgBr2, what are your 2 ions present? Magnesium and bromide. What is your concentration of magnesium? What? 0.25. What's your bromide ion concentration? Well, what? Okay. I heard a O. I just didn't know if it was the beginning or the end. But yeah, 0.5. Okay, it would be twice as much. Sodium carbonate. 0.33 molar sodium carbonate. Now take a look at that. Okay, remember what stays together and what doesn't stay together. Those carbon and oxygens are not going to split, right? They're part of the same polyatomic ion. So what would 0.33 molar sodium carbonate in terms of sodium, what would it be? Okay, and in terms of carbonate? Who got 0.9? Where'd that come from? Why'd you take it times 3? Yeah, but there's not a parentheses here with 3 of those. That 3 just goes with the oxygen, remember? So carbonate is actually 3 oxygen atoms and 1 carbon atom all stuck together to make 1 ion. Okay? All right. This one's a little more math. So iron 3 sulfate is this particular compound. So you've got 2 irons that will fall apart, so you double that. Okay? And the sulfate has 3, so you would triple that. Okay? There you go. So you were all right. Yay for you. Okay? I would do a toe touch, but I can't. So. Well, I guess I can. Funny, wasn't it? Funny. Okay. Now, similar to this has been easy because what we have been talking about is taking a solid, weighing it out, dissolving it, going directly to moles. To make a concentration of something, you just take moles per liter. All you got to do is weigh it out in terms of grams, and you got it. You can control it. However, what if I give you something that's already in aqueous solution? What if I give you, for example, I tell you to make, for our lab, we need 1 molar hydrochloric acid to run this experiment. But all I have is 12 molar hydrochloric acid. How are you going to make it? How do you make 1 molar from 12 molar? Can you make it? Let me ask you this. Can I make 1 molar hydrochloric acid from 12 molar hydrochloric acid? And then can I make 12 molar hydrochloric acid from 1 molar hydrochloric acid? Have you ever heard of any watering up anything? No. You water down stuff, right? You can take something that's, if you've heard of watering up, then I'm not talking about extracurricular activities or anything like that. You can take something that's concentrated and dilute it, right? In practical terms, anyways. And you can take something, of course, that's dilute and get rid of some of the solvent and, in a sense, concentrate it in that manner. But I'm talking about for practical reasons in a laboratory, you can go down, but you can't go up, right? So that's why I keep, like in our acid cabinet back there, that blue cabinet, there'll be a sheet on there that'll list a bunch of acids that are in stock solution, sulfuric, nitric, hydrochloric, and then whenever I need some acid, you go back there and you dilute according to what concentration you need. The difference here is that we are not starting with something, like when I go back and I get sulfuric acid to make a solution of it, it's not in crystal form. It's not like I go into the cabinet, pull it out, weigh it on the scale. It's already a liquid. Okay? So how do I then take something that's already a concentrated solution and make it a less concentrated solution? It's a little bit different. The math is slightly different, rather than just weighing something out and making a moles per liter solution. Okay, this is called dilution, and there is a specific math problem associated with it. It's not just 2 parts, 1 part like it is when you're cleaning around the house. Okay? It's much more precise than that, hopefully. It's a good thing that it is. Now, recall what I'm saying. I had a student in another class I was teaching. We were doing some demonstrations. It's for elementary teachers, how you can incorporate science in the classroom, bring some stuff in. And one of her demonstrations was about pollution on water, and she took a little drop of food coloring in a big container of water, and you put it in there, and it's sort of, and these are for little kids, remember, like first, second graders, you know. And you stir it up, and you can see that there's a little slight color of maybe pink in the water. And you know that that same drop is there regardless of how much water, right? However much stuff was in that drop, whether you put it in a container this big or a container the size of this room, you still have the same amount of stuff that was in that drop. It's just spread out more. And that was, kind of her point was then when she would add more and more to this giant container, and eventually you don't even see that drop anymore. It's so faint, there's no color, but is it still there? Yes, it's just all spread out now, right? So in terms of pollution, there might be a little bit of pollution, and it's so spread out in some of the water that we don't see it, and we don't detect it, but it's there, and it can still have adverse effects if it came in contact with things. Well, relate that to what we're doing here. What we're not changing here when we dilute something is we're not changing the amount of solute that's present. You can't, right? If I take in something that's concentrated and I try to water it down, is the same amount of solute still there? Yes, it hasn't increased, it hasn't decreased. What you are changing is the liters part of moles per liter. You're not changing the moles part, right? So you can manipulate the denominator. You can make more and more liters, and the more liters you make, guess what? The lower that number gets, the less concentrated it becomes. And you've spread all those molecules out, and it's not as potent as it normally was. That's what this is. It's a matter of how much do you spread it out, how much liters are you trying to make? How much water do you use versus actual solute that's present? Okay, so here's the formula that you'll use. It's really easy. I like it better. I don't like this one as much as I like my own. So write down the one I want to use. Okay? Because this one's out in words and it's easier to sort of see. But here's what I want you to use. M1V1 equals M2V2. It is? I must have put it on there and forgot. All right, well, write it down anyways.
Someone put it on there.
Hey, I put it on there. The M stands for molarity, concentration, right? V stands for gas, volume. 1 and 2 stands for initial and final conditions. If you know what molarity you're trying to get to, and you know how much of it you need, and you know what molarity you're starting with, then what you figure out is how much of this stuff, the concentrated stuff, how much of it do I want to pull out and then dilute up. Okay, I'll show you what I mean with the problem. what volume, for example, if I had a 12 molar, first of all, that wouldn't happen, but if I had a 12 molar solution of potassium chloride, you could never get that dissolved. What volume of 12 molar potassium chloride would be needed to make 5 liters of 1.5 molar potassium chloride? I have a stock solution. I have a highly concentrated form of, let's say, potassium chloride. What I want to do is make a much weaker version of that. I want to make 1.5 molar. Okay, so in order to do that, I've got to know what my concentration is that I want and how much of it I want to make, because that depends on how much I want to dilute, right? So, I mean, I got to know how much of it I want. I want 5 liters of it. So, when I'm done, I want 5 liters of a 1.5 molar potassium chloride solution, and the only thing that I have to work with is what you see here, 12 molar potassium chloride. I've got to dilute that. Now, what I don't want to do is just take this 12 molar solution and just start dumping water in it. Then I've wasted my entire stock solution. I can't use it for anything else. The whole point of this calculation is so that you can tap into this and figure out of that container, how much do you want to pull out? And then once you pull it out and drop it, then you can dilute that which you've pulled out, right? There's no point in wasting that. Then you've gained nothing by just dumping it all in a container that's already that. When I make up acid in lab, I don't take a giant jug of hydrochloric acid, concentrated, and then just dump it out into this giant tub and fill it up with water until it's dilute enough. Because we might need 200 milliliters for a lab, and I've just made 3,000 liters. I mean, that's ridiculous. That's not gonna work. All right, so we label what it is we know. We know that it's a dilution problem going from a stock solution to a weaker solution. So we're going to use M1V1 equals M2V2. Okay? Let's label what we know. What do you think this is? M1, M2, which one? That's M1. That's what we're starting with to dilute. What's this? Good. V2, M2. So we want V1. What V1 will represent is how much of this I want to pull out and use. Okay? All right, so we've labeled that. So that would be concentration of 1 times volume of 1. In other words, M1, V1. That's where that comes from. What I'm solving for is this, right? I want volume of my initial volume. So I can rearrange. I can put my numbers in. I can rearrange before I put my numbers in. It doesn't matter, whatever you want to do. But realize you've got to solve for volume and rearrange algebraically to do that. You can solve for 0.625 liters. That's what your answer is. So what does that mean? How then, without looking, I don't know if I tell you the answer or not, but how would you make this? If you now have calculated V1 to be 0.625 liters, how could you make this solution? What do I do? Okay, and then do what? Exactly. That's exactly what you do. You take 0.625 liters, take 0.625 liters of your stock, put it into a container, and dilute it the rest of the way to 5 liters. Okay? Good. So there's what it is. That's the long way about it. Pour in what you need, then dilute it all the way up to whatever size. If you don't need 5 liters, if you need something weird like 133 milliliters, then you'll have to do it like in a graduated cylinder or something where you can get, incremental measurements as opposed to just a big bulk measurement like this. It just depends on what you're doing. Okay. Oh, good. Stoichiometry. Are you excited as I am? Okay. Now, we know what stoichiometry means. It tells us the relationship between the number of moles of things that are reacting and that which is produced. It's constant ratios that help us tremendously. Okay? So here's hydrogen and oxygen reacting to form water. 2 moles of hydrogen, 1 mole of oxygen, 2 moles of water will form as a result. Okay? If we know that molarity is defined as moles per liter, what we can do, we've already solved this problem, sort of. What we can do is, if we know, like I said, molarity equals moles over liter. If we know molarity and we know liters, guess what we know? Well, I know because we just said I know molarity. If I look, molarity is equal to, whoa. Molarity is equal to moles per liter. If I know liters of volume, and if I know the concentration of what I am using, is there another variable that I can find out of this? I can find moles. If I know any of those two, I can find the third one. Okay? So that means another way to do chemistry now is to work off of solutions. If I tell you that you are going to mix in 25 milliliters of a 1 molar sodium chloride solution, you have a liters, you have a molarity concentration, you know how many moles you're reacting. Okay? So be able to go back and forth between those. That's what this next problem is going to be about. If you know the concentration of the solution you are using, and you know how much of it you're going to pour in, then you know how many moles you're putting in to make it react. All right, so let's take a look. How much 0.115 molar potassium iodide solution in liters is required to completely precipitate all the lead in 0.104 liters of a 0.225 molar lead 2 nitrate solution? Okay? You can do it. Okay? All right, now think about it. Let's break this down, taking everything that we've learned so far in other chapters as well, and see what this question is asking, because don't shake your head this way, shake it this way. Okay? We can do it. Now stop. Okay? Hammer time. Couldn't resist it. Anybody got hammer pants at home? Me neither. All right. Now, here's what we can deduce from this problem. There's a chemical reaction that's taking place. Yes? What is that chemical reaction? What are the products, etc.? Now, we go back and we think about, we did precipitation reactions. We did a lab where we formed precipitates. We looked at solubility chart and figured out, what things would be soluble, what things would be insoluble. What this question is asking. First of all, let's look at your equation. Let's look at the chemical reaction at hand. I'm using potassium iodide, right? Potassium iodide, and I want to precipitate all the lead from lead 2 nitrate. What that means is I'm going to have a lead 2 nitrate solution. I'm going to dump in potassium iodide, and what happens when you mix them together? See if you remember. We did this exact reaction. Anybody remember what color it turned? Bright color. Yellow. It was yellow. It was all yellow. And when the lead came in contact with the iodide from potassium iodide, this was soluble, right? It was an aqueous solution. This was a soluble aqueous solution. But when they came together, the ions could mix up. And when they did, you could get lead latching onto iodide. And when you did, you got a yellow precipitate that formed. So here's what this question is asking. It's saying, here's our equation. Okay, in our head, we know that you're mixing together potassium iodide in aqueous form, reacting that with lead 2 nitrate. It's given right here. In aqueous form. When that happens, what will the products be? Okay, this is implied in the question because it's a precipitation reaction. What? Well, no, listen, what does it mean? If you're going to add this to completely precipitate all the lead, that means you want to react all the lead. What are you going to use to react and pull that lead out and precipitate it? You're going to use iodide ions, right? So what this is asking is, how much of this do you got to put in so that you react all of this? That's what this is asking. Okay? So, if you want to completely precipitate all the lead ions, that means you want to react this, whatever ratio you need to react it with, so that you can pull apart all of these lead and put all of it into solid form, so that none of it's still floating in solution. Okay? That's what it means to completely precipitate all the lead ions. Okay, so if that's the case, and you know that you're precipitating lead from this, and you're using that to do it, then this has to be your equation. That means you should know the products. We've already covered that. What can switch places? This and this. Are any nitrates ever insoluble? No, they're always soluble. So if you have potassium nitrate, It's just going to be an aqueous solution of ions floating around. It's not going to be a solid. You're going to precipitate out the lead. It's going to react with the iodide. That's going to be your solid that forms out. And since it's lead 2, because this is a 1 negative, there's 2 of them, so that must have been a lead 2, 2 positive. That means it's going to be PbI2. Plus I tell you at the top. Okay? So, now we balance the equation. Here's it all balanced. 2, 1, 1, 2. That means that I'm going to need twice as much in terms of moles. I'm going to need 2 moles of this to react with every 1 mole of this to get everything precipitated out, to make this reaction work perfectly good. Everything cancels out. Okay? Got it? Good. All right, now, the only thing I'm missing and what I need to know before I can ever use this equation, what unit do I have to use in this equation? What's the only thing I can use in chemical equations? Moles. Can I get to the mole values that I need? I have concentrations and volumes. That means I have moles. Okay? All right, so I don't know the liters on this one, so I can't go to moles from that. But here's what I can do. Once you have only one of these, that's all you need, right? Because you can use stoichiometry to go from one to the other. So here we go. 0.104 liters of a 0.225 molar lead 2 nitrate solution. What can I do to get to moles? Remember this. We know this to be true. So what can I do? Okay. Would I multiply those? Divide those? What? I would multiply them. To get moles, I bring that up. So I multiply those two together, and I would get a value in moles. Okay? So I've got moles right here. Moles of lead 2 nitrate. Now whatever I use for that, right? Whatever I get for that value, I know that there is 1 of these for every 2 of these. Okay? So what I can then do is use this to calculate the number of moles of this that has to react. Right? Once I know the number of moles of this, and I know the molarity of that, guess what I can find? The liters. I can find the volume, and then I know how much to pour in to make this reaction happen. What? That's right. We've come back full circle. Okay? Now, one more time. Now, make yourself feel good with this. Don't make yourself feel bad. You should feel good that you understand this problem. Okay? Think of, if I would have thrown this up the first day, you had a what? And there's nothing. You know what how much meant. That's maybe all you would have got out of this. Okay? But we've come so far. Let's put it all together. Okay? Let's realize we can answer this question. What is it? My wife got back from Guatemala. How do you say how much in Spanish? What do you say? I don't remember. Anyways, all right, so let's read it. How much of this concentrated solution of 0.115 molar potassium iodide, how much of that do you need in liters in order to completely precipitate all the lead that is in 0.104 liters of a 0.225 molar lead 2 nitrate solution? Does it make any more sense the second time? Ah, well. All right, so here's what we're going to do. We're going to utilize stoichiometry to make this happen because we have to know the ratio. How much of this reacts with how much of this? Okay? All right, can I get a mole value to use this with? Yes, and the answer is right here. I can take this times this to get moles. So liters times molar to get moles. That gives me a mole value for this compound right here. Then you can realize that whatever mole value I get, I set up a 1-to-2 ratio, and then I can get a mole value for this. Once I get a mole value for this, I know moles, I know concentration, I know liters. Okay?
So is this going to be a partial credit question where we write down some of that? No.
All right. So here's the steps that we said. Now we're just going to plug in our numbers. All the arrows, all the paths. Yeah, I don't like these either. They don't help me. Yeah, but I don't know, maybe they help somebody. But anyways, here is our 0.104 liters times the molarity, like you said, which is 0.225 moles per liter, right? So that's going to get us to moles of lead-2 nitrate. Now, once we're at moles of lead-2 nitrate, we use stoichiometry. We know that for every 1 mole of that reacts, 2 moles of potassium iodide will react. Now we're at moles of potassium iodide. I need to get to volume, to liters of potassium iodide. I can do that because I know that molarity is 0.115 moles per liter. I can position that in a way to where these units cancel out, and I can get a final answer. With sig figs, 0.407 liters. Okay? To go through that, practice it, see if you can follow it. Why do we do that? Why do we put salt on the roads? How does that work? Why do we use antifreeze? Is antifreeze and coolant the same thing? So how can it be antifreeze, but yet still coolant? It's one of these. So it's half and half. So we pour half and half in.
With some water in it too.
Yes, it does. Ice can be melted, so to speak, in a way, whenever we dump salt on it. Because what happens is when you take water, it normally has a boiling point of 100 degrees, right? 100 degrees Celsius. When you put something in that water, whatever it is, you dissolve something in that water, you interfere with the freedom of the water molecules, and you interfere with their normal behavior to the degree that what will happen is the boiling point will actually have to be you'll have to reach a higher point in order to make it boil now. Okay? So you will take, like if you dump salt into water, take salt water, take take salt water and take pure water, boil them, you will find that the temperature that you have to reach to make pure water boil is a lower temperature than what it will take to make salt water boil. It takes a higher temperature to make salt water boil. Why is that the case? On the same note, if I take those same samples and instead of boiling them, decide to freeze them, what will happen is I can freeze the pure water at 0 degrees Celsius. I'll have to get it even colder to freeze the salt water. Okay? So when you add particles to the solvent that is normally by itself, you expand the window. If this was freezing point and this was boiling point, you shift it in opposite directions. You make the freezing point lower, you make the boiling point higher when you put stuff that's dissolved in these solvents. Okay? So that's the whole point of the whole thing here. You've always got a little bit of a solution of water when you have ice. So what you're doing is dissolving some of that salt in with the snow and the ice and the water, the friction, the cars are rubbing on it a little bit, putting it into solution. And what happens is it creates a solution that doesn't freeze at normal freezing points. It would have to be colder, even colder outside before it starts to freeze. Okay? So it's not like it's technically melting it, it's just preventing more freezing to occur. And then normal melting is occurring with friction and sunlight and that kind of stuff. Okay? Now, we in our car, of course, can use antifreeze, which is the same thing as, you're right, engine coolant, because it can go both ways. It drops it, it makes it require a colder temperature to freeze, but yet requires a higher temperature to boil. It allows, that way, it doesn't, if you just filled up your car with water in your radiator, and it got really, really hot, then it would just, turn to steam and it would boil very easily and it becomes more dangerous and not as efficiently, it doesn't cool as efficiently. But if you have antifreeze running through there, it can absorb more heat, more energy, and not boil over near as easily as what water can. And at the same time, when it's really cold outside, if you just had water in there, you run the risk of freezing things up, right? Whereas with antifreeze, it can get colder and still not freeze. So hence the name, anti-freeze. Ethylene glycol is the main component of antifreeze. That's starting to change a little bit. You can get some propylene glycol antifreeze. You can get safer versions of it, but still, I mean, it's toxic, right? So you don't want to spill it out if you got pets and stuff. Huh? What's the difference between what? Ethylene and propylene? It's how the carbon is positioned on the chemical. It's just a subtle chemical difference. Okay, so we know this, like I just said. You can change the melting point and freezing point of something by adding a solute to it. We call these colligative properties. Colligative properties means properties that are associated with the concentration of something. For example, the more salt that you put into that water, the more you affect its freezing point and its boiling point. The less you put in, the less you affect it. Since that's dependent entirely upon the amount present, we call that a colligative property. Okay? Well, you can, yeah. The more you add, the more you drop the temperature. But realize that outside you don't need to keep adding more and more to compensate for a change in freezing point, because it's not like the weather's going to drop 15 degrees every day. You know what I mean? So I mean, the weather's only going to drop so far. You just kind of keep adding more because it. Right. Okay. What's interesting is it doesn't matter what the solute particle is. What matters is the solvent, how well it usually crystallizes. It doesn't matter if it's sugar or salt that's in the water. It'll sort of affect it pretty much the same way in terms of its boiling and freezing point. Something I was going to add to that. What was it? Oh, like when you cook, I mentioned this before, like cook spaghetti. Why? Some people actually can put salt in the water whenever you do that. What this allows you to do is actually get your water at a hotter temperature than normally would be. Remember when I said you have a pot of water and you crank it to boiling? Once you get to 100 degrees, it's not going to change until all that water goes to steam. Well, that means that if you're cooking a pot of spaghetti and you don't put anything in it but pure water, you're not going to get a temperature hotter than 100 degrees to cook that with. Okay? Because as long as you have the lid off of it and gas can escape and all that kind of stuff. But if you put salt in there, what will happen is you will get a hotter temperature. It takes a hotter temperature to get to boiling. So you can get the water to take, to set around it. I don't know what the temperature would be, 101, 102, 103, whatever. It's at least a little bit higher than what it normally would be. Okay, and that could cook it a little better, I guess. I'm not a chef. I don't know how all that works, but. No, it causes the freezing point to go down. It goes from like 0,
and the freezing point would be like
-4 now.
Okay. And so you're causing the boiling point to go
Up. Freezing point to go down, boiling point to go up.
All right.
Right.
Well, that's going to say regular water.
Right. Right. Well, that's interesting. That's a little bit different. When you put, when you get to boiling starches and carbohydrates, they actually leach out certain proteins when they're boiled that interfere with the escaping of the gases, and that's what causes them to boil over, much more like potatoes and spaghetti and that kind of stuff. So it's a little bit something different. It's not necessarily a colligative property. Well, because it allows those. It allows it to get, the process itself that causes all of that is still the same, but what the salt will allow is sort of to spread that out a little bit more, affect the boiling point enough to where it's easier for those bubbles to escape, is the easy answer. I can't go into all the chemistry, but I don't know all of it, but even some of it I can't go into. But it's sort of related to this, but the actual frothiness that's associated with that bubbling is actually because of a leached out protein from the starchiness of those compounds that you're actually boiling. So, okay. Also when you make homemade ice cream, right? You put rock salt in there to get it colder. It makes it colder. You put salt in there, you lower the freezing point. So say instead of a 0 degrees Celsius, now you can get it down to -2, 3, -4, maybe more, I don't know, degrees Celsius. You can get it colder. So, okay, so whenever you're dealing with colligative properties like this, an easier way to measure this instead of moles per liter is something called, instead of molarity, it's called molality. One letter difference. Okay? Molality, I didn't make these rules. Molality is a little m instead of a big M. Okay, so molarity is a big M, moles per liter. Molality is a little m, which stands for moles of solute, just like we had before, but instead of liters of solution, you have kilograms of solvent. Now why? Just to make it harder. No. In this case, remember I'm talking about colligative properties, we care about the solvent. We're changing boiling and melting point of the solvent. That's what we're referring to. So instead of dealing with the entire solution, we want to be able to have something that focuses just on the solvent. So we have moles of solute per how much kilograms of solvent are present. Okay, that's why we're dealing with this. Now, how can we get the mass of the solution? Remember, if we know volume and we know density, grams per milliliter, for example, you can go, if you know how much of it you have, if you weigh it and you know the and you know the density, then you can go from grams to milliliters or vice versa. So density can be a conversion factor that we may have to use at some point. All right, so how do you calculate molality? You've got a solution containing 17.2 grams of ethylene glycol, antifreeze, dissolved in a half a kilogram of water. What is the molality? What is molality? Moles of solute divided by the kilograms of solvent. Do I have kilograms of solvent? Yes. Do I have moles of solute? But can I get it? Yes, I can convert that. If I know the formula, I can convert that to moles. So that's what I'm going to do. Okay? There's the molar mass of ethylene glycol, so I'll use that to convert. So here's my mass of solute. I'm going to convert that from grams to moles. My mass of solvents, remember that's what's doing the dissolving, so water is already there. It's half a kilogram. Now I just got to divide those two together. Or by each other, whatever I meant. Okay, so there you go. 17.2 grams of ethylene glycol. Converted to moles is the quantity that you see there. To calculate the molality, take that moles divided by a half a kilogram of water, and you get a molality of 0.554 little m, ethylene glycol. Okay? So it's moles of solute per kilograms of solvent. We convert, here's our solute, convert that to moles. Here's our kilograms of solvent, which it is dissolved in. It's already there. Okay? Good. So like I said, we can do a freezing point depression. Now here's what's cool. Not only can we say we've lowered it, you're going to tell me and calculate how much you lower it. That's right. You're going to take the freezing point depression. You're going to tell me how much you have depressed the freezing point, by how many degrees. What will your new boiling point be? What will be your new freezing point? That kind of stuff. Okay? So first we'll look at freezing point. Freezing point depression. It's going to be directly proportional to your concentration of your molality concentration. The more concentrated it is, the more of an effect you're going to have on your freezing point. Here's the math. The change in the freezing point, which is this right here, right? Delta TF. The change in the temperature of the freezing point is equal to the molality concentration times a constant. Easy math. You got to look up the constant or I give it to you. So all you got to know is what the concentration is. Look up the constant for whatever solvent you're dealing with and then calculate. Okay? Here are some common constants. They'll be, you don't need to go through this. They'll be given to you. I'll tell you what they are, or else you can look them up in the book to do your homework. You look up, make sure, it's very important that you pick the right one. For example, look at water. Here's the freezing point, normal boiling point, right? 0 degrees freezing, 100 degrees boiling. If you are doing a freezing point depression and you want to know how its freezing point is affected by a solute, Do not pick KB. That stands for boiling. Pick KF. That stands for freezing point constant. So you're going to use this number. If you want to test and see how much of an effect it's going to have on its boiling point with this stuff added to it, then you use the boiling point constant, which is 0.512. So make sure you understand which one of those you're calculating in your problem. I'll give you that information, yes. Okay, so here we go. How does antifreeze work? Calculate the freezing point of a 1.7 molal ethylene glycol solution. So if I put that concentration of ethylene glycol into my automobile, as opposed to just using pure water, how much of a difference can I make in the freezing point? Okay, that is necessary to clog me up. All right, so we know that there's what we need. There's our equation. Do I know molality? Skip this right here for now. Do I know molality? Yes, I do. It's 1.7. Do I know the freezing point constant of ethylene glycol, or can I look it up and find it? Yes. Yeah, somebody will tell you you'll look it up something. So that means it's simple. I just got to multiply those two things together. Now, here's the key, though. What this solves for is not your new temperature. What this solves for is the change from the original temperature. Okay? So what that means is, if I'm going to calculate the change in the freezing point, remember which direction I always go, right? If it's the freezing point, it's going to go down to a lower freezing point. If it's at the boiling point, it's going to go to a higher one. So if I calculate the change in the freezing point to be 3, and we're dealing with water as my solvent. Water normal freezing point is 0, and I calculate this math to get me an answer of 3. It's a negative 3. Okay, that's my answer. Remember that. You'll get confused if you don't. If I was doing boiling and I calculated my delta TB to be 3, what would my new boiling point be? 103. Remember, we go up with boiling point. We go up with boiling point. We go farther away from the center. We go up with boiling point, down with freezing point. Okay? All right, so in this case, we plug in our numbers. That's kind of confusing, so we just don't worry about that. Take 1.7 times whatever the freezing point constant is for, well, in this case, it should have been, go back. Hang on a minute. 1.86 for water. See that? Now, here, hang on, 1.86 here for water. Realize what you're doing. Ethylene glycol, is it the solute or the solvent? Solute. What are we affecting? Solute. What are we affecting the boiling point or the freezing point of? A solute or a solvent? Solvent. So whatever constant you use is in reference to your solvent, not your solute. So if I say ethylene glycol solution, unless it's otherwise specified, that is dissolved in water. So you're going to use water as your solvent. Okay? All right, so you get 3.2 degrees Celsius. What that means is you've changed it by 3.2 degrees. So in this case, it would go from 0 degrees Celsius to negative 3 degrees Celsius. You see, that's a big benefit. Okay? All right. You do the same thing with boiling points.